Wow. Our next speaker is Florian Luca, who talks about multiply gleeful numbers. Florian, please.
Hi, everyone. Thank you, Mel, for the opportunity to speak at this conference. I have good memories about the New York Number Theory Seminar. I gave one in May 2024 when my daughter was graduating from NYU, and that was great. So I apologize for not being there to be with you guys in person, but I had some other commitment this week. So anyway, today I'm going to tell you about multiply gleeful numbers and this notion. I've heard it last year at the Integers Conference in honor of Mel and Carl Pomerantz's 80th birthday. And at that conference at the University of Georgia, there was Jonathan Sorensen. He gave a talk about this notion. So let's see what this notion is. What is a gleeful number? So let us take a positive integer n and an integer k, and let's write f sub k of n to be the number of representations of n as a sum of k powers of consecutive primes. So you want to be able to write n as the sum of k powers of primes, which have to be consecutive in the sequence of prime numbers. Apparently, this question was first studied by Moser, who took s sub k of x to be the summatory function of f sub k of n for n running up to x. So you basically count all sums of consecutive primes up to x. And he shows that f sub 1 of x is asymptotically x times natural log of 2 as x tends to infinity. And I believe that this is the only value of k, namely k equal to 1, for which an asymptotic is known. For k bigger than 1, there are upper and lower bounds for this function s sub k of x. And they appear, for example, in some recent work of Sarah Moore and Jonathan Sorensen of last year. There's a preprint on the archive. And that preprint also presents various heuristics concerning positive integers n such that both f sub k of n and f sub k prime of n are positive. For k prime different than k and both at least 2. So you want a number n, which you can write as the sum of consecutive k powers of primes and of consecutive k prime power of primes. Okay, so let's call the positive integer n to be k gleeful, or gleeful, we can omit the k, if f sub k of n is positive. So if it is a sum of k powers of consecutive prime. So let's take a look at the counting function of that. So in this paper in 2024, these three authors, O'Sullivan, Sorensen, and Stahl, they show that if k is at least 2, then the counting function of the k gleeful numbers up to x, it's of order of magnitude x to the exponent 2 divided by k plus 1, and then you lose some logarithmic factor, log x to some other exponent, 2k divided by k plus 1. And if x is sufficiently large, then this quantity is sandwiched between two multiples of this order of magnitude. So let's prove, for example, the upper bounds, just to have something to prove, which is unconditional. Suppose that I write n as the sum of L kth powers of consecutive primes, with the smallest one being p sub I, and n is at most x, then certainly if I sum up p sub I to power k with itself L times, then so namely L times p sub I of to the power k is at most x, therefore p is at most the kth root of x over L and is a prime. So what do I need to do? I need to sum up the summatory function of the primes, so pi of the quantity kth root of x over L, for my running index L being as big as it can theoretically be. Let's call that capital L, which is neither a reasonable bound for capital L. You apply the prime number theorem, the number of prime up to somewhere, it's somewhere divided by the log of that. It turns out that the logarithm of the kth root of x over L, of course, you can pull the 1 over k out and you get the log of x over L. And this capital L is small with respect to x. So it's smaller than x to some power smaller than 1. So up to constants, the logarithm of the kth root of x over L is the same as the log of x. This explains, let's say, the second middle term there, where log of x is there, and you just sum up the reciprocal of 1 over L to the power 1 over k up to the largest L can be, which is capital L, and you get x to the 1 over k capital N to the 1 minus 1 over k divided by log x. And you say, well, how large can L be? Well, trivially, the largest possible value for L is if I sum up all the first L primes to power k, I should get something at most x if L is attainable at all in this way. So the left-hand side of that sum is, of course, the next value, the p sub L to the power k plus 1, again divided by some logarithmic factors. And then you get that the capital L to the power k plus 1 times some logarithmic factors. So that's the L prime times some logarithmic factors at most x. So certainly capital L is at most x to the 1 over k plus 1, as promised, that capital L is smaller than x to a power smaller than 1. So now I go back to the first displayed inequality. I stick that upper bound for L in there, and I get this upper bound that I promised. And you can also do some similar argument for the lower bound. Now let's interpret this in some way. Let's forget about the logarithmic factors, and let's just say that, well, the number of k gleeful numbers up to x is roughly x to the exponent 2 over k plus 1, plus little o of 1 if you want. You can bury some little o of 1 in the exponent. And we can interpret this by saying that the probability that n is gleeful is the counting function of them dividing by all n's up to x, which is x of them. So it's roughly 1 over n to some exponent, alpha k, whose limiting value is 1 minus 2 over k plus 1. So this is for one value of k. Well, now suppose that we are looking for gleeful numbers, k numbers n, which are both k gleeful and k prime gleeful. And then Mori and Sorensen, they conjecture that if k is at most is smaller than k prime, and k is greater or equal to 3, or k prime is greater or equal to 5, then there should be only finitely many n's with the property that they are both k and k prime gleeful. And this is based on the fact that the probability, let's say, that n is k gleeful is 1 over n to the alpha k. Therefore, the probability that n is both k gleeful and k prime gleeful, assuming these two events are independent, should be roughly 1 over n to the alpha k plus alpha k prime. And the sum of these two exponents is 2 minus 2 over k plus 1 minus 2 over k prime plus 1. And if k and k prime are both large, so k is at least 3, therefore k prime is at least 4, or k is at least 2 and k prime is at least 5, then this amount is bigger than 1. So now you're basically summing up the sum of the reciprocals of n to some exponent larger than 1. That series is convergent, so by a classical heuristic, you'd say, well, maybe there are only finitely many examples. Of course, if you make k prime equal to 3 or 4, there are this amounts that is written there, alpha k plus alpha k prime, is smaller than 1. So then they conjecture that maybe there are infinitely many n, such that, let's say, f sub 2 of n is bigger than 0, and also f sub k prime of n is bigger than 0. And actually, they have an example for 2 and 3, which is the number 23,939, which is simultaneously a sum of 3 cubes of consecutive primes starting at 17, and a sum of how many of them are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 primes, squares of primes starting at 23. So what I'm going to tell you today in the maybe 10, 15 minutes that I have left, I'm going to show you a conditional proof, which is different from the heuristical proof that they present, that maybe indeed f sub 2 of n times f sub 4 of n is positive infinitely often. And what we are going to use for our condition is Schinzel's hypothesis H. What does Schinzel's hypothesis H say? Suppose that you have k polynomials which have positing leading terms and are irreducible. So potentially they could represent simultaneous primes infinitely often. And suppose that also they satisfy some tame local condition with respect to small primes, namely that for every prime, there is a value of n which doesn't divide any one of these evaluations, f sub 1 of n, f sub 2 of n, f sub k of n. So assuming that you have k polynomials like this, then the conjecture predicts that there are infinitely many positive integers n such that all of them are primes. Now, of course, the local condition, which looks like you have to do infinitely many checks, it's in fact a finite condition. Because the point is that the polynomial f1 of x times f2 of x times fk of x has some degree, which is the sum of the degrees of all those polynomials. And now if p is a prime which is bigger than this sum of degrees, then of course that polynomial cannot have more roots modulo p than its degree. In particular, there will be a non-root modulo p of that polynomial. So in particular, you just have to check the condition that p doesn't divide f1 of n, f2 of n, f sub k of n, only for finitely many p's. And these finitely many are given in terms of the sum of the degrees of the involved polynomials. Okay, so our result is the following. Assume Schinzel's hypothesis H holds, then there are infinitely many positive integers n such that f sub 2 of n, f sub 4 of n is bigger than 0. And actually, there are other versions of Schinzel's hypothesis H, which are quantitative versions, which are, for example, the Bateman-Horn conjecture. The Bateman-Horn conjecture predicts that under the same hypothesis as the Schinzel's hypothesis H, not only do we have infinitely many n such that f1 of n, f2 of n, up to f sub k of n are simultaneously primes, but it predicts an asymptotic for the number of n's up to x with the property that all these polynomials are simultaneously prime. And maybe unsurprisingly, the prediction is that the number of such guys, it's x divided by log of x to the power k, how many polynomials you have. And then, of course, there is some constant term there, which is maybe like in the previous talk that encodes the local information, which is the singular series. So let's go ahead and see how are we going to do this. So I'm going to challenge you to find a better construction than I did. So for my construction, as I said, if you apply the Bateman Horn conjecture, not only get infinitely many n's up to the quantity x, you get about x to the 1 over 50 of them. And that somehow it's a little bit smaller than what you would get if you would plug in the values 2 and 4 into this sum of the reciprocals of the n's to alpha 2 plus alpha 4. So we aim to construct positive integers m now, which are our n's, which simultaneously have a representation as a sum of 25 consecutive squares of consecutive primes and simultaneously a sum of 25 fourth powers of consecutive primes. And for those consecutive primes, since I'm applying the Schinzel hypothesis H, you would probably guess that I will choose some generic polynomials and I'm going to choose them to be linear polynomials. So I'm going to have 25 polynomials. I'm going to say that the middle polynomial is called x. And then the polynomials before x and after x, they are going to be x minus a sub I and x plus a sub I for I equal 1 to 12. So what I have there, I have 25 linear forms, with the middle one being x, and then there's symmetric ones below and above x. And then I calculate the degree 4 term. Because I chose them in such a way, the degree 3 and the degree 1 terms of that polynomial go away, and I get 25x to the power 4 plus 12 sum of ai squared x squared plus 2 sum of ai to the power 4. And then I want to complete a square there, so I do what I do in school, in secondary school. I complete a square. I look at the quantity 12 sum of ai squared divided by 10, which is 6 over 5 sum of ai squared. I complete the square. I get 5x squared plus delta, everything squared plus mu, where mu is the number that you see displayed in there. And now I look at the quadratic side. For the quadratic side, again, I take linear forms. There are still 25 of them. The middle one is called y, and the other 24 are centered, y minus b sub j and y plus b sub j for some values of b sub j. And I calculate the sum of the squares of those guys, and I get 25y squared plus 2 sum of b sub j squared. So now I look at m of x and n of y, which are displayed there, and I want them to be the same polynomial. So I say, okay, well, if you want to do that, then probably your best bet is to assign to 5y the value 5x squared plus delta. And then also you want to know that the number nu, which appears in m sub x, is the same as twice sum of b sub j everything squared. And then numerically, you can choose these a sub i's the way they are displayed there. You choose a delta, you calculate what delta is, you calculate what mu is, you calculate mu over 2, which is that number, and you have to write mu over 2 as a sum of 12 distinct squares, and you write it as a sum of 12 distinct squares. If you think that that was brilliant, it wasn't that brilliant, it was quite easy. To write it as a sum of 12 squares, what I do, I took kind of 8 big squares, so that if I sum up these 8 big squares, then I get a number that's smaller than the number that I'm shooting at. After removing those 8 big squares, which were 1,700, 1,701, and so on up to 1,707, I get left a number which is much smaller. And I apply Legendre's theorem that that number is the sum of 4 squares. And of course, I go to the computer and I ask them which ones are, show me a representation as the sum of 4 squares, and it gives it to me. All right, very good. So now we have the numerics. So now with this choice, so I have the numbers b sub j's, which are displayed there for j equal 1 up to 12. And I have y is x squared plus delta over 5, which is x squared plus 4056. And now one feature that you have to notice of this is that, let me go back, this system is sort of homogeneous in the sense that I can replace the AIs by AI times some number capital lambda. And I can replace the B sub j's by the B sub j's times the square of capital lambda. And these equalities are still valid. And this introduction of the capital lambda, I will really need it because you see the way I chose these B sub j's, I even chose them consecutive. But you can't really aim to shoot at primes. You can't really ask for nn plus 1 and n plus 2 to be primes infinitely often. And I did choose the b sub j consecutive. But if I modify the b sub j's and I multiply them by something else, where something else includes contributions from all the small primes, for example, is a number that's even divisible by 3 and 5 and so on, then I'm going to be fine. And I can make those things to be simultaneously prime under the Schinzel hypothesis H. So with this observation, therefore, I'm going to replace a sub j by a sub j times lambda, b sub j by b sub j times lambda squared. And now I have those p sub j of x, which are 25 of them that are displayed there. And I have the q sub j of x, which are other 25, which are displayed over there. And I say, well, can I make them simultaneously prime? Well, I take lambda to be the product of all the primes up to 75, and that's my lambda. And now I take this polynomial to be the product of p sub j of x, q sub j of x for j equal 1 to 25. It's a polynomial that has 50 factors. 25 are linear, 25 are quadratic, so it has degree 75. And reduced modulo small primes, it looks like x to the power 75. So modulo every small prime, this polynomial has only one solution, namely 0 modulo p. And modulo primes which are bigger than 75, I'm using the trick that since I have a polynomial of degree 75, which is even monic, if I reduce it modulo primes which are bigger than 75, it's going to have a non-root. So in particular, Schinzel's hypothesis H, the conditions of Schinzel's hypothesis H are fulfilled, and therefore I can find infinitely many n such that p sub j of n and q sub j of n are primes for all j equal 1 to 25. And this gives me that identity in there. And you say, okay, fine, maybe you convinced me. However, there is another requirement there. The requirement is that these p sub j of n's and q sub j of n's are not any old primes, but they have to be consecutive in the sequence of prime numbers. Now we have a good chance of them being consecutive just because the P sub j of n's, they are all cornered in an interval, right? Because they are all of the form x minus a sub j for certain values of a sub j from 1 up to 25. So they are all cornered in the interval, let's say a sub of length a sub 25 plus a sub 1 or something like this. But however, we do have to make an argument there. And the argument to make there, what we do, we basically throw in some Chinese remainder lemma. So how are we going to throw in some Chinese remainder lemma? As I say, all these primes, they are basically linear functions in n, which all have the same leading coefficient. So maybe it's 5n plus minus something and or n plus minus something, and in such a way that they have bounded gaps. So now all I want to make sure is that when I evaluate in such n, there is no evil additional prime that sits between the primes that I have already arranged, because that would destroy the condition that these are indeed consecutive. So what I do, I look at the interval where those guys sit. That's the interval, let's say, that I have to shift. And I throw away the linear functions, which I already know that they have to be primes, and I'm left with some other linear functions, which I want them to be composite. So suppose that I have k of them. I label them U1, U2, UK. And then what I'm going to do, I'm going to choose a bunch of primes, all of them bigger than 10 to the fifth time lambda squared, which go increasingly just to fix some ideas, and such that the polynomial x squared plus uk has an integer root x sub k modulo r sub k. And then I do the same thing for the linear guys. For the linear guys, they are also trapped in an interval of a bounded length. And I looked at that interval from minus 123 lambda to 123 lambda. And then I eliminate the forms that I want to be primes, which are the q sub j's for j equal 1 to 25. I look at the remaining numbers. I choose again primes larger than 10 to the fifth time lambda square, which are distinct. And then I use the Chinese remainder lemma in such a way that for those primes, I'm going to choose an n congruent to x sub 0, where x sub 0 plus v sub l is congruent to that particular prime s sub l. So now what I have here now, I solve all this with the Chinese remainder lemma, and then I get this big progression. And this progression has the property that if I evaluate my polynomials in that progression, then the intermediate polynomials cannot represent primes because I pick them in such a way that each one of them is divisible with some prime, which I labeled either R or S. And then you say, yes, but now you have destroyed the Schinzel hypothesis age. And I say, no, I didn't destroy the Schinzel hypothesis age. The reason being that those polynomials that I have, I just apply an affine transformation to those polynomials. They still remain irreducible. They still have positive leading terms because if you stick in a linear function inside an irreducible polynomial, you stick in a linear function in x, then you can't create a non-irreducible polynomial unless, of course, you take the linear function to be somehow 2x and the last coefficient is even or whatever. So you introduced some prime, and that's why the polynomial is not irreducible, but otherwise it is. So in fact, there is something else that's lurking here, which I didn't want it to write down, but this is a very easy lemma to prove. Namely, suppose that you have two sets of polynomials, f1, fk, let's say the f's, and the g's, which are g1, gl. And now the f1, fk satisfies the Schinzel hypothesis age requirements. They satisfy those conditions. And then the other polynomials, which are G1 up to GL, the only thing that you know about them is that they are non-constant and they have the property that that family of polynomial is disjoint from the F. So they are just different polynomials. Then you can prove that the Schinzel's hypothesis H, in fact, implies the more general statement, where the more general statement is that there exist infinitely many n's, such that simultaneously f1 of n, f2 of n up to f sub k of n are primes, and for the same n's, g1 of n, g2 of n up to g sub l of n are simultaneously composite. And this is basically what it's lurking in here in order to ensure that the primes that we have chosen for our construction are in fact consecutive primes. And these G1, G2, GL are kind of the intermediate polynomials. And this statement, it's not very hard to prove. It's based on the fact that if you have a non-constant polynomial, then and you evaluate it in n's, then the set of prime factors, of values of these polynomials, is infinite. So these are the set of primes that you can work in pretty much the same way as I did now using some Chinese remainder lemma. And that's basically what it is. And as I said, if you count this, so basically what you have this polynomial, you have these things which is written as sum of fourth powers of things which have to be up to x. This means that the input n, where you evaluate those, has to be at most, let's say, t to the 1 over 4. And then you have 50 of them. So if you do the if you do the Bateman-Horn heuristic, then you get that my construction gives you under the Bateman-Horn that the number of such values, it's roughly t to the 1/4 divided by log t to the power 50. And that's all I have to say. Thank you.
Oh, thank you very much, Florian. Are there any questions for our speaker? No. If
So
not,
my challenge to you guys is to find a better construction because you see this was a bit arbitrary, summing up 25 things in both sides. Maybe you can find sort of shorter sums because what I would like to do, I would like to be able to find some examples, but you see the way I'm having it, I'm having 50 polynomials which should be simultaneously prime. I don't even want to attempt to search for an n with those properties, but if you have fewer polynomials which have to be simultaneously prime, then maybe you can succeed and maybe you can find interesting examples. And that's all.
comments or questions? If not, thank you again, Florian.
Thank
And our
you.
next talk will be in 3 or 4 minutes.
Thank you.
Thank you.